Good morning, everyone. Welcome back. Welcome back. I'm going to give people a few minutes as they trickle in before we officially get started. But in the meantime, just a summary of what we're going to cover today. It's going to be a lot. We have to do all of integration in just under 3 hours. So we have about an hour and a half of standard level content, and then we have an hour and a half of only HL content. All right. So we're going to talk about how to find antiderivatives, all the ones that you're supposed to know, both the standard and higher level, the techniques that you need to know for finding advanced integrals, both at the standard and the higher level, applications of integrals, so that includes finding areas, but also kinematics. And at the higher level, we'll talk about volumes of revolution. Um, so yeah, there's going to be a lot to do. So what we're not doing today are the simple little exercises. I don't have time to give you, a minute here and there to try very basic things. Instead, we're going to focus on exam style problems. We're going to do a lot of hard questions. And if you want to do exercises, they're still going to be available on the website for you to practice after the session. But in the interest of time, we're going to have to move pretty quickly. That also means for the problems, I'm only going to give you a couple of minutes to basically get a head start on the problems that we try. I don't have time to give you the full length of time to solve the problems on your own and then solve them. So the way I'd like to do this is I'm going to give you 2 minutes or 3 minutes to start the problem. You work on paper and you try and get a head start compared to me. And then I'm going to keep going and explain it. And as long as you stay ahead of me, you can continue working on the problem on your own. And if you're stuck at any point, you just hop back and watch the recording. So with that said, let us get started. Okay. So we're going to start with this notion of reverse differentiation, also called anti-differentiation. Um, and basically, that's just the opposite process of differentiation. So if I have a function whose derivative is f, then that's the antiderivative of f of x. All right, and we often write this with a capital F. It's not a common notation in IB, but generally speaking in math, people denote the antiderivative by a capital F. And that, in particular means that if I take the integral of dy by dx, if I take the derivative, the integral of the derivative of y with respect to x, and I integrate that with respect to x, I get y. So this equation is what tells you that integration and differentiation are opposite procedures, all right? And you should notice this little dx under the integral. That tells us which variable we are integrating with respect to, okay? Now, at the standard level, it's always going to be dx. At the high level, we'll also see integrals that are in dy, okay? So the slide I showed you a second ago was actually technically incorrect in some way because I forgot the integration constant. And what you have to realize is that if I have a function, let's say it's capital F, right, whose derivative is f of x, then if I did f of x plus c, its derivative would also be f of x because the derivative of a constant is f. Which means that when I take an integral, the answer that I get, I could actually add any constant and it would still satisfy the derivative relationship that we talked about on the previous slide. Which is why every answer that you put, unless it's a definite integral, which we'll talk about later, has to have the plus c. Now, sometimes you'll be given specific conditions, we'll talk about that on the next slide, that allow you to solve for c. But in general, if you just want to find the integral, don't forget the plus c. Here's an example. If I have f of x is equal to x ln of x squared, its derivative is 2 ln x plus 2. Okay, so the integral of 2 ln x plus 2 is f of x plus c, so it's x ln x squared plus c. I now have this new constant. I don't just get the original function back. Okay, so antiderivatives that you're supposed to know at the standard level. You have to know how to find the integral of x to the power of n, and you just reverse the power rule that you have for derivatives. So the power increases by 1 because when you differentiate, the power decreases by 1, and you divide by n plus 1 so that when you differentiate this, the n plus 1 in the exponent cancels with the n plus 1 in the denominator. So for example, the integral of x to the 5 is x to the 6 over 6 plus c. Now, you also need to know how to integrate sums of functions or scalar multiples of functions. So if I have some constant times a function and I'm integrating that, the constant comes right through the integral, and I have the constant times the integral. Something similar for sums, if I have the integral of f plus g, that's the integral of f plus the integral of g. And in general, if I combine these two rules, and I have this what I call a linear combination of f and g, which is some multiple of f plus some multiple of g, I can say that's a multiple of the integral of f plus a multiple of the integral of g. And we use that to integrate all sorts of polynomials. So let's say I have the integral of 2x cubed minus 1 over 5x squared. Well, I take out the 2, Okay, I have integral of 2 times the integral of x cubed minus 1/5 of the integral of x to the minus 2. And that it brings me to half of x to the 4 plus 1 over 5x plus c. Okay. Now, like I mentioned, sometimes you're going to have boundary conditions, and those boundary conditions will impose a particular constraint on C. So let's say we're told that a function has the derivative x minus 1, and we're told that f of 1 is equal to 3, and we want to find f of x. So if I know the derivative, I can find the form of the function by integrating. So I integrate 4x minus 1, and I get 2x squared minus x plus c. But since I know that f of 1 is equal to 3, I plug that in and I get 2 minus 1 plus c is equal to 3. It means that c is equal to 2. And so my function is f of x is equal to 2x squared minus x plus 2. More antiderivatives. Again, the IB decided to distinguish between the power rule for integers and the power rule for rational numbers. It's the same thing, but now you can apply it for square roots and slightly more complicated powers of x as well. Derivatives of sine and cosine. Well, we remember that integrals of sine and cosine. We remember that the derivative of sine is cosine, and the derivative of cosine is negative sine. And so I can say that the integral of sine is negative cos plus c, and the integral of cos is sin x plus c. Also, the integral of e to the x, this one's easy. It's just e to the x plus c, because the derivative of e to the x is e to the x. Derivative of 1 over x is ln absolute value of x, and I think it's worth quickly showing you why that is. I'm going to sketch a picture of 1 over x and of ln of x, because students always ask, why is there an absolute value on the ln? That doesn't make any sense. Okay? We know that the derivative of ln prime is 1 over x. But here's the thing. Natural log has a domain of x greater than 0. So the domain of ln of x is x greater than 0, right? That's the domain of ln, but 1 over x looks something like this. If I were to graph 1 over x, I'll do it in a different color. 1 over x is the reciprocal function. Here, we'll do it like this. 1 over x is the reciprocal function, and it looks like this. All right? So its domain is everything except for 0. So it's not defined at 0, but it's defined for every other real number. And in particular, it actually does exist over here. It has a slope over here. So when I integrate it, the answer that I get needs to also have a domain that is all the real numbers. And remember that the derivative is the way that I find the slope of the function. So if I'm finding the integral, basically I'm finding a function whose slope is the y-coordinate of the function that I'm integrating at every point. And that means that because 1 over x is an odd function, the slopes are just going to be opposite each other. So what I'm going to end up having is simply a function that looks something like this, right? It has the opposite slope. I mirror the line ln of x onto the other side of the y-axis, and I get a curve that now has exactly the opposite slope of ln of x on the other side, and that is exactly what I want for the integral of 1 over x. So just a quick note as to why I have an absolute value in there. Now, the integrals of the form f of ax plus b. We're going to talk in a second about a technique called u substitution, and you can always do these by u substitution, so I don't need to necessarily worry about this formula, but it is oftentimes a shortcut if I see if I consider the function, g of ax plus b, and I take its derivative, that is, by the chain rule, a times g prime of ax plus b. So as soon as I have the integral of some function of f of ax plus b, some function composed with a line, that's just going to be 1 over the antiderivative of f at ax plus b. So maybe that looks confusing. I'll show you an example of why that would be useful. If I have sine of 3x minus 2, then I can just say, oh, it's going to be negative cos of 3x minus 2 with a 1 over 3 in front, because when I differentiate this, the 3 would come out. Now, it's just a technique or a rule that allows you to do this next technique more quickly. In other words, skipping some of the steps and saving some time. But this next technique does actually cover this as well. And that technique is substitution. So notice that if I compose f of x, f of g of x, right, with some constant, and I'm adding a constant, which doesn't make a difference, and I take its derivative, according to the chain rule, I'm going to get g prime of x times f prime of g of x. And that means that if I have an integral which is the form some constant k times g prime of x f prime of g of x, then I realize that's going to give me k times f of g of x. Now, oftentimes it's a little bit difficult to see how that I would apply that. It's a little bit more useful to make the substitution u is equal to g of x. And then that means that g prime of x is du by dx. Then I can write my integral as k du by dx times f prime of u dx. And notice that I have du by dx and then dx. And so the dx's are going to cancel, and I'm left with k times f prime of u du. And very, very often, we're going to know how to integrate that using our elementary formulas, okay? So to find the correct u, what you should do is search for the one part that is almost the derivative of another part. And what I mean by almost is because there's a constant k that doesn't really change anything sometimes, but you should be looking for, there should be one thing that's like a derivative and it's inside of some other thing, some other type of function. It could be in an exponent, it could be in a square root, it could be in a fraction, but you should see one thing that looks like the derivative of another part of the integral. Okay, and I have a question in the Q&A. What if it's sin of 3x squared plus 3x plus 2? Do you use the substitution method that you're showing? So that integral is a very, very difficult integral to solve. You would have to do some fancy thing. I'm not actually sure how you would solve that integral. I could show you, I mean, if you had the integral sin of 3x squared plus 3x plus 2, you can't use this technique because there is no the derivative of that inside piece, right? If I wanted the derivative of the inside, I would want 6x plus 3 somewhere. Now, if I had 6x plus 3 in front, then I could integrate that. That I know how to do. But if the 6x plus 3 is not there, then I'm a little bit lost. That's difficult, okay? I'm sure it's a possible integral, but I don't think it's a clean one. It's definitely not one that you need to solve on the IB. Okay, so here's an example of what you might have to solve on the IB, something like the integral of 3x times the square root of x squared minus 1. So I recognize that the derivative of x squared minus 1 is 2x, which is a constant multiple of 3x. So if I let u be equal to x squared minus 1, that gives me du by dx is equal to 2x. And then my integral becomes 3 over 2, because I have the 3, and I take, my derivative gives me 2x. So I have 3 over 2 times du by dx times the square root of u dx. And then when I cancel the dx's, it becomes 3 over 2, the integral of u to the power of 1 over 2 du. I know what the integral of u to the power 1/2 is. It's u to the 3/2, and that actually cancels. I have this 3/2 in front, which is perfect, plus c. And if I put back in x squared minus 1 for u, I find x squared minus 1 to the 3 over 2 plus c. Okay, first IB style example. I'm going to give you, let's say, 2 minutes to get a head start on me, and then I'm gonna solve this. Okay, I think that's enough time. So I'm looking for the integral of e to the 2x over 1 plus e to the x, and the question tells me to use the substitution e to the power of x. Now, this is an important thing in IB. If you don't have an integral that is obviously of the form g prime of x, f of g of x, f prime of g of x, if you can't immediately tell by looking at it what the substitution should be, then they're going to actually tell you what substitution to use. So that's the good news. You only have to know how to pick your u when you have something of this form. Now, let's actually do that. If I say u is equal to e to the x, then du over dx is also equal to e to the x. So I can say dx is equal to e to the x. Dx is equal to du over e to the x, I should say, is equal to du over e to the x. Now my integral, the integral of e to the 2x over 1 plus e to the x dx, I can now rewrite as the integral of u squared, because that's e to the 2x, over 1 plus u, and then times, and remember, since e to the x is u, this is du over u. So this just becomes du over u. I replace that for dx, and then I have the integral of u over 1 plus u du. Now, still a little bit tricky to solve. What I have to do here is I'm going to say that this is going to be equal to the integral of, and this is a bit of a weird trick, but I can say this is 1 plus u minus 1 all over 1 plus u. And I do that because then I have one thing that is going to be equal to the denominator, so I can just have that be 1. And then the other thing is going to be minus a constant divided by 1 plus u, which is going to be much easier to deal with. Okay, so then that becomes the integral of 1 minus 1 over 1 plus u du, which is equal to, the integral of 1 is just going to be u, excuse me, and then the integral of 1 over u I know is ln of u, so this is going to be minus ln absolute value of 1 plus u, and let's not forget our plus c. Okay, and I just have to plug back in what I know for u, which is that this is e to the x minus ln of 1 plus e to the x plus c. Okay, so I'm just going to clear my screen now, and we're going to check that off. So we found this. Okay, so we had e to the x minus ln of 1 plus e to the x plus c. Now, sometimes the question might ask you to realize, but they would specify this in the question and give your answer in the form, that since 1 plus e to the x is always positive, I don't actually need the absolute value here. It's not going to make a difference, but it's fine with or without the absolute value in this context. All right. And now we're told that a function has the derivative e to the 2x divided by 1 plus e to the x, and it has a y-intercept of 3, which means that f of x is going to be equal to the integral I just found with some specific value of c that I can find. So this is e to the power of x minus ln of 1 plus e to the x plus c. And if I plug in 0 for my y-intercept, I'm going to get e to the 0 minus ln of 1 plus e to the 0 plus c, and that should be equal to 3. E to the 0 is 1, so this is minus ln of 2 plus c is equal to 3. And that means that c is equal to 2 plus ln of 2. All right, so I just write my final result, which is that f of x is equal to e to the x minus ln of 1 plus e to the x plus 2 plus ln 2. Okay, that is my answer. Now something a little bit harder. I don't know why this is marked as higher level. The SLs can do this. Standard levels can do this, but it is a hard question. First, we're going to prove the identity cos squared is equivalent to 1 plus cos 2 theta over 2. So let's remember that cos of 2 theta is equal to 2 cos squared theta minus 1. So 1 plus cos 2 theta over 2 is equal to 2 cos squared theta over 2, which is cos squared theta. All right, and that proves the identity. And now the question says that we can use the substitution x equal to sine theta to solve the integral of the square root of 1 minus x squared dx. Okay, so let's write what I know. That's going to be equal to the integral. I'm going to rewrite now. Oh, well, I'm going to also write if I say x is equal to sine of theta, then I can differentiate with respect to theta and say that dx by d theta is equal to cos of theta. In other words, dx is equal to cos theta d theta. Okay? Now I differentiate with respect to theta because I have x is equal to something and not the other way around. And I want to find what I'm going to replace my dx with. So in this case, I want d theta. And then I'm going to replace x in the integral with sine of theta. So I'm going to have the square root of 1 minus sin squared theta. And then I know that dx is cos theta d theta. Right? Now, I also know that the square root of 1 minus sin squared is cos squared, according to the Pythagorean identity. And so this is going to be, when I square root that, it's going to give me cos theta. And it's multiplying another cos theta. So that gives me cos squared theta d theta. All right. Now, I still don't really know how to solve that. But what I can do is use the identity that I found in part A to rewrite that. So what's that going to look like? I'm going to take cos squared theta, and I'm gonna put 1/2 outside so that I don't have to deal with the inside, and it's gonna be 1 plus cos of 2 theta d theta. And that I do know how to integrate. That's 1/2 of the integral of 1 is gonna be theta, and then cos 2 theta is gonna be half of sine 2 theta. All right. Now, the question was in terms of x, which means we want an answer that's in terms of x. I know that theta is, so since x is equal to sine of theta, theta is going to be equal to arc sine of x, I can say. Okay, so theta is going to be equal to arc sine of x. That's one thing. And then sine of 2 theta is 2 sine theta cos theta, which is equal to 2x times, because x is sine theta, and cos theta is the square root of 1 minus sine squared, so 1 minus x squared. Okay? So if I rewrite everything that I have now, this is going to become half of arc sine of x plus x square root of 1 minus x squared. Okay? That is my answer. Tricky question. I'm not totally sure why it's tagged as high level, because the standard level students could do this question. It'd be a hard SL question, and more likely to show up for HL than for SL. But SL students, I think you should be able to follow all the steps that I did there. I just used standard level identities and standard level integrals. So I'm going to move in the direction of definite integrals now, which is setting up the connection between integrals, areas, and how they connect to each other. So I want you to imagine in this picture that I have a function and I'm considering it between the lines x equal to a and x equals to b. I want you to imagine the area under that curve. And what's happening in this little animation is that a bunch of rectangles are being used to approximate the area. And the number of rectangles is changing. And you can see, I think, by looking at when the number of rectangles is small, like right now, there is a pretty major difference between the area of the under the curve and the area of all the rectangles added together. But as the number of rectangles increases, it looks like it's pretty much exactly the area under the curve. And that's exactly how integration works, how we find the area under the curve. We divide it up into n rectangles, okay? So we say that delta x, which is the base of each rectangle, is whatever the total width is here, b minus a. We divide that up into n pieces. So each triangle has a base of b minus a over n. And then the height of each triangle, the height of each triangle is going to be f of some multiple of that difference, okay? And it should actually be a plus that. So it should be f of a plus k times the difference, right? K times delta x. So we start at we start here, and then we go across one by one, okay? Now, and I'm going to sum that over k is equal to 1, 2, 3 for every triangle. And I can thus express my approximation as a summation, something like this, okay? And you don't need to know this formula at all. I'm just giving you this so you have some intuition about how these integrals work. Okay, so I have this sum, and that's exactly how this approximation is being calculated. And what I do is I say, okay, now let's take the limit as n goes to infinity, because I can tell that my approximation gets better the more rectangles I have. So let's imagine what happens when I get towards infinitely many rectangles. And what happens is this delta x becomes infinitesimally small, and we replace delta x with dx. Okay, so dx is like a delta x, it's just for an infinitely small d. And the sum becomes an integral. So the integral is actually a curly s in, I think it's Greek. So there's a sort of foundational connection between those two things, where the integral is kind of an infinite sum with minute infinitesimal pieces. Okay, and instead of having bounds from k is equal to 1 up to n, I just put my bounds as the lower bound of x and the upper bound of x, so a to b, like that. This is in your formula booklet, and it gives you the area under a curve. So how do you actually do definite integrals? Let's say you've evaluated the antiderivative of f of x. What does it mean to have bounds on it now? It just means that you do the antiderivative at b minus the antiderivative at a. Okay, so you plug in first b and you subtract what happens when you plug in a. What you should also notice is that the integration constant no longer matters, because if I do f of b plus c and I subtract f of a plus c, you're just going to get f of b minus f of a. The c is not going to do anything. I'm going to skip that example because it's pretty basic. Another thing to bear in mind is that if you have done a u substitution, you have to be very careful with your bounds, right? If I change from x to u, then I'm no longer going to have necessarily the same bounds. Now I have two choices. Let's say I do my u substitution. I find the antiderivative is f of u for some function. I don't know what it is. And my bounds are from x equals a up to b. I have now two choices. I can either plug x equals a and x equals b into the equation for u, and I can find the bounds in terms of u, or I can replace u with x, with whatever it is in terms of x, and actually just use the boundaries for x. So here's an example. I'm not going to show you how you would do the integral, but let's say I had 2x over x squared plus 1, and I do a u substitution with u is equal to x squared plus 1. That leads me to the answer ln of the absolute value of u from x equals 1 to x equals 3. Now, if I put u equals x squared plus 1 back in, I would get ln of the absolute value of x squared plus 1, and I just plug in 3. That gives me ln 10 minus, if I plug in 1, ln of 2, that's ln 5. The other choice is to say, well, if x equals to 3, that means that u is equal to x squared plus 1 is 10, and if x is equal to 1, then u is equal to 2. And then I just change my boundaries to be 10, from 2 up to 10. And they're both going to give me the same answer, and you can do whichever one you're more comfortable with. Now, I also want to explain, because students often have this question, why is it that the integral, or the area under the curve, is also the antiderivative? Why is it that I can take this opposite of the derivative, and that is somehow related to the area? So what I want you to do is think about the area under this curve here, and I'm going to call it x because it's the area from some unknown starting point up to some specific value of x. So it's all this area here. And let's remember that the derivative is defined as the limit as h goes to 0 of some function, of f of x plus h minus f of x divided by h. In this case, my area is a, and I want to think about the derivative of a. Let me zoom in. Okay, so if I take the area x plus h, then I can express that as an integral from just this, basically this change in area here. And if when I add a little bit of h, when I change the x value, I'm basically adding on. Hang on. I'm adding on this small piece of area, right? This orange piece of area here. And what I've drawn in black is a small rectangle that has the height f of x, and its area is basically, it's pretty close to the area of the entire orange region. And as I let this difference, h, go to 0, you'll notice that the difference between those two becomes smaller and smaller, and the orange area becomes more and more approximately rectangle. Okay? And so what does that mean? It means that the since I care when I'm looking at the derivative at the difference, the difference between the function at x plus h minus the function at f, and dividing that by h, that difference is this area. And when I divide that area by h, I have an area that's approximately rectangle divided by the base, which of the base of that rectangle, h, should give me the height of that rectangle, right? And so what does that look like formally? Well, if I have, area from x plus h, area of at x plus h minus area of x, that's this integral from x up to x plus h, so this little area here of f of x. And I can say that's approximately, but under the limit, it is exactly going to be h times f of x, because the area becomes a rectangle. And so when I divide by h, I just get f of x. And that means that the derivative of the area is just the value of the function at that point. And that kind of makes sense. The rate at which the area is changing is proportional to, and is exactly equal to, how high the function is. So if the function is at 0, if it's lying along the x-axis, and I go a little bit to the right, I increase x, the area is not going to change because I'm already at 0. But if I'm really, really high above the x-axis, I'm at like x equals to 1,000, one small change in x massively increases my area. So with that said, we now have this formula, we have a method for finding the area under the curve. We're going to take the integral of a function f of x between the bounds a and b, where a and b are the left and right bound of the area that we're interested in. Now, often you're not going to be told what those boundaries are. Instead, you're going to be told, oh, find the area enclosed between this function and the x-axis. And you're first going to have to find where the function intercepts the x-axis. So here's an example. If I have y is equal to 1 minus x minus 3 squared, I can find that it intercepts the x-axis at 2 and 4. That's just using quadratic skills. And therefore, my area is going to be the integral from 2 up to 4 of 1 minus x minus 3 squared. If I expand all that, I just get a quadratic, and I know how to integrate powers of x, and so this leads me to my answer of 4 over 3. Okay? Now, IB style example. I'm going to give you 2 minutes to get a head start over me, and then we're going to continue. So I have in a diagram the function f of x is equal to negative 2x minus a divided by the square root of x squared minus ax plus 25, and a is some unknown. And this area looks almost like a triangle, but it's not exactly a triangle, unfortunately. Otherwise, our life would be a lot easier. But it might happen. It's sort of like a possible theme on the IB where you have a function that looks a lot like a triangle, and they'll ask you, in part A to find the area using integration, and in part B to approximate it as a triangle and like maybe compare the error. That's something, a kind of trick that the IB might pull. So what I have to do first is find what the value of A is, because I can't integrate with this unknown, otherwise I'm going to have a bit of trouble. And what I can say is, well, I realize that I have a y-intercept of 4 over 5, so f of 0 should be equal to 4 over 5. And in particular, f of 0 is equal to, it's going to be negative 2 times 0 minus a over the square root of x squared is going to be 0, minus ax is going to be 0, so it's just going to be over the square root of 25. Okay, so this is going to be a over 5. And that means that a is equal to 4, because that's supposed to be equal to 4 over 5. 4 over 5, so a is equal to 4. All right, not so bad. And then, with that done, now I can set up the integral. And my integral is going to be, I need to find the x-intercept first. So now I have in the numerator, I have 2x minus 4, which is equal to 0 when x is equal to 2. So this is going to be 2 right here. That's 2. So now my area is the integral from 0 up to 2 of 2x, and I'm going to put the minus outside because it doesn't really make a difference. 2x minus 4, that's this minus, that I'm putting outside. 2x minus 4 divided by the square root of x squared minus ax plus 25. Now, and a I said was equal to 4. We found that. Now, this tells me, this already is screaming at me substitution, and it's screaming at me substitution because I see that in the numerator I have 2x minus 4, which is hopefully the derivative of what I have in the denominator. Let's check. If I had u is equal to x squared minus 4x plus 25, then du by dx would be equal to 2x minus 4. Oh, beautiful. That's exactly what I have in the numerator, which means that I can write du is, and sorry, this is supposed to be a dx here. Let's not forget the dx. du is equal to 2x minus 4 dx. And so my integral can be written negative the integral, and now I'm going to make sure that I write my bounds as x equals to 2, x equals to 0, so it's clear that I'm not talking about bounds on u. And I'm going to replace this as du over, and I just have the square root of u. Okay? Now the square root of u is u to the power of 1/2. So its integral is 2 over 3 u to the 3 over 2. Okay? So I'm going to have now, sorry, it's a minus 1 over 2. What am I saying? This is minus 1 over 2 because it's 1 over the square root of u. And so the integral is just going to be u to the 1 over 2, with a 2 in front to cancel the 1 over 2 that comes down. Okay, so this becomes negative the square root of u from x is equal to 2, and there's supposed to be a 2 in there, sorry, 2 square root of u from x is equal to 2 down to x equals to 0. And because u is a big, rather large equation, x squared minus 4x plus 25, I'm actually going to just change my boundaries into u. So I'm going to say that u of 0 is equal to, well, that's just 25. And u of 2 is equal to 2 squared minus 8. So that's 4 squared minus 4 minus 8 is negative 4 plus 25 is 21. Okay? So what do I end up with? I end up with negative 2 times, and I plug in my boundaries now. I plug in the 2 one first, so square root of 25 minus the square root of 21, which is equal to, because the minus sign is going to flip everything, I'm going to have 2 root of 21 And then the root of 25 is 5, so I'm going to have minus 2 times 5 is minus 10. And that is my answer. And I'm just double checking because I think I maybe made a sign error. Yes, I did make a sign error because the boundaries in U, when they swapped, the larger one became the lower one. So I actually had to do the square root first of the one at 2, so square root of 21 minus square root of 25. So this is actually 10 minus 2 root of 21. That's my final answer. Okay? So that was for the area under a curve enclosed with the x-axis. But in general, you have to know how to find the area enclosed between a curve and the x-axis. And that includes areas where the curve goes below 0. Now, because in this region the function is negative, the integral here, if I were to integrate from m to b, I would find something that's negative. But I am interested in the area, which means I want the absolute value. So what I have to do is I say that the area is the integral from a up to b of the absolute value of f of x. Okay? Now, if you have a calculator and it's a calculator question, you can just plug that into your calculator, and maybe I should show you how to do that in a second. But if you don't have your calculator, then you need to split the integral up into two parts, the part where it's positive and the part where it's negative. So I do from 0, integral from a up to m of f of x, and then I do plus the integral from m to b of minus f of x so that I get a positive area there. Okay? So here's a little example. If I have the curve x cubed minus x, it's going to be negative, or it's going to be positive for -1 minus x less than 0, and then negative for 0 less than x less than 1. So I split it as the integral from, and that should be minus 1 up to 0 of x cubed minus x, plus the integral of 0 up to 1 of negative x cubed minus x, and if I do all of that, it leads me to the answer of 1 over 2. Another one that you need to know how to do is the area between two curves, right? So you have two curves that intersect somewhere, A and B, and you're trying to find the area between them. So we use the formula, the area is equal to the integral from A up to B of the absolute value of f of x minus g of x, because the heights of each of the points in the triangle are f minus g, but at some points g is bigger than f, so we have to have an absolute value there. Okay? So if I was looking for the area enclosed between x cubed and x, well, the curves intersect when x cubed equals x. That means that either x equals to 0 or x is equal to plus or minus 1. And I have to test which one is bigger and when. So if I do x cubed minus x, for when x is between -1 and 0, that's going to be a positive number. And when x is between 0 and 1, it's going to be a negative number, which means that I can split it as the integral from -1 up to 0 of x cubed minus x plus the integral from 0 up to 1 of negative x cubed minus x. And again, that all leads me to the answer of 1 over 2. Okay, time is up. Let's go over this. Well, time is not up, but at least the head started. So I have a function, f of x is equal to x times cos of 2x squared. And I have a line with the equation y is equal to mx. And it intersects the curve y is equal to f of x at x is equal to square root of 3. Okay, so let's first show that m is equal to minus 1 over 2. So if the curve intersects at square root of pi over 3, that means that f of square root of pi over 3 is equal to m times the square root of pi over 3. Okay, the lines are equal there. And what is f of the square root of pi over 3? Well, the x is just pi over 3, so pi over 3. And inside of cosine, I have 2x squared, so x squared is pi over 3. And cosine of that, or 2 times that is 2 pi over 3. Cosine of that is negative 1 over 2. So that times negative 1 over 2 is equal to m times root of pi over 3. And so m is equal to minus 1 over 2. All right? And now we have the region enclosed between the curve f of x, the line L, and the lines x equals to plus or minus root 3, so between here and here, is shaded in the diagram below, and we want to find the area of the region. So we need to set up the integral. The integral from negative root pi over 3 up to root pi over 3. And by the way, if I know that this is pi over 3, I know this is root pi over 3, a negative root pi over 3, because f is an odd function, and the line is also an odd function, but for standard level students who don't know what those words mean. I just have a squared in here, which means cosine is going to have the same value, x is going to have the opposite value, and so they're going to meet on the opposite side as well. All right, so I know that it's that. These are my bounds, and the area is going to be, well, I need to put an absolute value, and I need to do x cos of 2x squared minus root pi over 3x. And the slope is, what am I saying? That's not the slope. The slope is minus 1 over 2, so I do minus 1 over 2. X is plus 1 over 2 x dx. Now, I could split this integral in the middle and do two different integrals, but I can also realize that both of these areas are the same by symmetry. They're both exactly the same area. So I can actually just take 2 times the integral from 0 up to root pi over 3 of the right-hand one. So the one here, which is where cosine is bigger, so I can just do x cosine 2x squared minus half of x dx. Okay? And okay, now we can try and integrate this. I'm going to have to use, first I'm going to separate this into two integrals again. I'm going to say I have twice the integral of 0 up to root pi over 3 of x cos of 2x squared dx, and then I'm going to have minus the integral of x dx from root pi over 3, from 0 up to root pi over 3. Now for this integral is just going to be x squared over 2, so that one's easy. X squared over 2, but the other one is going to be a little bit harder. I'm going to use the substitution u is equal to x squared because I have x outside, which is almost the derivative of x squared. So du by dx is equal to 2x, or in other words, dx is equal to du over 2x. And therefore, my integral becomes 2 times the integral from 0 up to root pi over 3 of, well, my x times dx is going to be canceled because I replaced dx with d over 2x, so I'm going to have just cos of, and sorry, I wanted this to be 2. I wanted a 2u squared, so that this made, that would have been better. So cos of u is 2u squared, which means du by dx is 4x, which means dx is du over 4x. So now I have cos u times 1 over 4 du. Okay, because I have a 1 over 4 here. Now I'm going to make some room, and we're going to continue. Let us do it over here. Okay, still just minus x squared over 2 from root pi over 3 down to 0. Okay, and just a reminder that u is equal to 2x squared, so we don't forget. U is 2x squared. And now I'm going to have basically 1/2 of the integral of cos of u, if I factor out the 1 over 4. And the integral of cos of u is sine of u. So I'd simply have half sine of u, which is sine of u is sine of 2x squared. Sine of 2x squared. Then I have minus x squared over 2, and that is all happening from root pi over 3 down to 0, right? And now we're getting pretty close to our final answer. I can now take, I can say 2x squared. So x squared is going from, or in other words, root pi over 3 squared is pi over 3. So I have sin of 2 pi over 3, which is, that's root 3 over 2. So it's root 3 over 2 times 1/2, so root 3 over 4. Minus, and then if I square x and divide it by 2, that's minus pi over 6. Minus pi over 6. And then I have minus, did I say something wrong? Oh, sorry, this was supposed to be a plus. It was a plus because the slope was negative. And so I made a mistake throughout. The plus is all the way here. That was supposed to be a plus pi over 6. And then at 0, sine of 2x squared is going to be sine of 0 is going to be 0. And x squared is also going to be 0. So this is the entire area. That's the answer. So some rules for definite integrals. And some of these are pretty obvious. But if you have two definite integrals that have the one has an upper boundary the same as the lower boundary of the next, then I can merge them into the integral from a to c of f of x. And that's just basically saying that if I have this area plus this area, well, that's just the area of the whole thing. And I can also work backwards. I can split an integral into two areas. And we kind of already know this from even just the previous problem that we did. But I'm bringing it up because the particular problem I want to do using those rules, and that problem is next. Okay, so I'm going to give you, 2 minutes to try this on your own, and then we're going to continue. Okay, so I'm given that the integral of a function f of x from 1 to 4 is equal to 6. And in part A, I want to find the integral from 1 to 4 of 3 times f of x, all right? And that is not difficult. That's just going to be, the 3 comes out, and it's going to be 3 times the integral that I know, which is 3 times 6 is 18, okay? Now in part B, I'm trying to find the value of the integral from 0 up to 1.5 of 2 times f of 2x plus 1 minus 3. All right, so what I'm going to do is I'm going to take that integral, the integral from 0 up to 1.5, and I'm going to say, I don't have to do a u substitution, but it's going to make my life easier. I'm going to say u is equal to 2x plus 1. Now du by dx is just equal to 2, and so dx is equal to half du. So my integral can be written as the integral of 2f of u du, then minus the integral of 3 dx or du. It doesn't really matter which one you do. Okay? And I'm going to change the boundaries. On this one, I'm going to leave them at 1.50 because I'm integrating with respect to x. But here, my boundaries are changed. Now I have u is equal to 2x plus 1, which means now if I plug in 0, I get 2 times 0 plus 1 is 1, and 2 times 1.5 plus 1 is 4. And that's good because I recovered the original bounds that I had. Otherwise, I was kind of hopeless with the bounds of 0 and 1.5. Now, the integral, and remember, these are, those are integrals in terms of, u. And therefore, I can write this as 2 times the integral of 1 to 4 of f of u du minus 3x from 1.5 down to 0. All right? And this is exactly the same thing as I'm given in the question. Whether it's u or x makes no difference. So this is just 2 times 6 is 12. And I'm subtracting out minus 4.5. 3 times 1.5, okay? And therefore, if I do that, I'm going to get 12 minus 4.5. And am I forgetting something? Yes, of course I'm forgetting something. That was silly. I forgot that du is half of dx, so dx is equal to half du, so I need to have it over 2 here. So that's not supposed to be 12, that's supposed to be 6. And that gives me 1.5. Okay? Okay, now we're getting to kinematics, which is I know a tricky topic for a lot of people. But the first thing I want to talk about is this word displacement and the word distance. The difference between displacement and distance is that displacement tells you the change in position over a certain interval of time, whereas distance tells you the total distance that you have traveled in that time. So in particular, if you follow a path that kind of loops back on itself, your distance is the entire length of that path, whereas the displacement is only what's the difference between one end of the loop and the other. So it's possible to come back all the way to the same point to have covered a very large distance, but to have a displacement of 0. Okay, those two words are important to bear in mind when we are going to talk about how to find these things with calculus. And what I want you to remember is that distance doesn't really care about the direction at which you're going at any particular time. It just adds up all the changes in position over all time, and no distance can cancel another distance. But it's possible to have to go in one direction and come back, and for the displacement to cancel. So how do I find, what can I do with my displacement? Well, if I take the derivative of displacement, that's going to give me, remember the derivative tells me the rate of change. The rate of change in displacement, let's say that I'm leaving my house, and the rate of change in my displacement, I'm leaving my house at 3 meters per second. That's my speed, or my velocity, to be particular. My velocity is the derivative of my displacement, okay? And velocity in particular has a direction. It can be positive or negative because I can be coming back towards the thing that I'm displacing myself away from. So I could be, as soon as I'm walking back towards my house, then the rate of change in my displacement is negative, and so I'm going to have a negative velocity. I can also take the derivative of velocity and find the acceleration. And the acceleration just means like how it is defined as the rate of change of the velocity. So it's in your formula booklet as a is equal to dv by dt is equal to d squared s by dt squared. Because not everyone takes physics, so not everyone really knows or thinks about what the acceleration is. But everyone knows what velocity is, so this is not going to be in your formula booklet. You should know and you should understand what velocity is. So let's take a look at an example, which says that s, the displacement, is equal to 4t cubed minus t, and that's in meters. And I want to find the velocity and the acceleration when t is equal to 1 second. So the velocity is the derivative of the displacement, which is 12t squared minus 1. And so when t is equal to 1, that's 12 minus 1 is 11 meters per second. And the acceleration is the derivative of the velocity, or the second derivative of the displacement, which is 24t. And so when t is equal to 1, it's 24 meters per second. Now, speed. What is the difference between speed and velocity? I can't have a negative speed. So whether I'm running or driving away from my house or driving back to my house, I'm going to be going at the same speed. And so the speed is the absolute value of the velocity, okay? Now, how can I find the displacement if I know the velocity? Well, because we said that the displacement was that velocity was the derivative of displacement, then displacement has to be related by the antiderivative to the displacement, to the velocity. And so I can find the displacement by integrating the velocity between the starting time and the ending time, okay? And so I want you to imagine that so I have my velocity looks something like this. The displacement that I'm going to travel is the area under the curve, okay? And one way to kind of, ground that understanding is to imagine a a procedure where you start, at a pretty high velocity, you go to velocity 0, and then you come back to with the opposite velocity, exactly symmetrical, such that these areas are equal. Okay, so that's equivalent to like driving to school and driving back. Those two areas are going to cancel each other, and your displacement is going to be 0. So that's one way to kind of remember, first of all, that the displacement can be 0, that it can cancel back with itself, but also to understand in a very intuitive way that the displacement is the area under the velocity curve. Okay, now the good news is this is in your formula booklet. So if you're looking for the displacement, you can actually just do the integral. And for example, if I have a velocity of 3t squared minus t, then the displacement between t is equal to 1 and t is equal to 3 is the integral from 1 to 3 of 3t squared minus t. And I just do nothing that we haven't talked about today, just normal integrals, and I find 22 meters. Now, how about the distance from the velocity? Well, remember that the distance is a little bit like the displacement, except that it doesn't really care about the sign or the direction that I'm going at any particular time. And so, if I had the diagram that I had earlier, the distances are not going to cancel here. Here, they're going to add. I want the total area. And we already know that to find the total area, we have to put an absolute value inside the integral. Because again, the distance only cares about how my position is changing. It's going to add up all of these little segments, and it's not actually going to cancel itself out when you change direction. So you have to put an absolute value, and if you don't have a calculator, that means you're going to have to split your integral somewhere in the middle and do it in 2 pieces. Okay, so if we're trying to find the distance covered between t is equal to 1 and t equals to 10 with a velocity of 5 minus 10, I would split the integral at the point where v is positive and the point where v is negative. So that's from 1 to 5 of 5 minus t, plus from 5 to 9 of negative that, so t minus 5. Okay, and if I do all of that, bit of tedious algebra that we're going to learn nothing from, is I would get 16 meters. It's very important in these kinematics questions to put your units, okay, because it's fundamentally a physical thing that we're talking about, so we need those units. All right, now time for an IB question. Often on the exams, these will be on the paper 2, so with calculator. But I think we will learn more from doing a no calculator question, because doing integrals on a calculator is very, very easy. And actually, I haven't shown you an example of that, so I probably will do that right after this slide. I'll show you how to find integrals on your calculator. Okay, so I'm going to give you a 5-minute head start on this, and then we're going to solve it together. All right, let's go. I have a particle x moving in a straight line, and its velocity v in feet per second from the origin after t seconds is given by v of t is equal to 3t squared minus 12t plus 9. It's worth noting that because the IB is an international syllabus, they want you to be familiar with all kinds of units, even though feet per second is an inherently stupid unit. So to find the initial velocity of particle x, which is what we're trying to do in part A, I just plug in t is equal to 0 into the velocity. So I do v of 0 is equal to 3 times 0 minus 12 times 0 plus 9. So I just get 9. Okay? Now, in part B, I'm trying to find the times at which the particle x changes direction. Okay, so the particle changes direction when v is equal to 0. Or in other words, 3t squared minus 12t plus 9 is equal to 0. So t squared minus 4t plus 3 is equal to 0. I can factor that by inspection. It's t minus 1, t minus 3 is equal to 0. So the times are t is equal to 1 second and 3 seconds. Okay, those are my times. Now, part C. The velocity reaches a minimum when t is equal to q. Okay, so I have a quadratic 3t squared minus 12t plus 9. And that has a minimum when x is equal to negative b over 2a, the axis of symmetry. So in particular, it's equal to negative 12, so 12 over 6 is equal to 2 seconds, halfway between the roots, I will also note. So I have q is equal to 2 seconds, and now I have to plug that into v to show what the velocity is at that point. So if I do v of 2, I'm going to get 3 times 2 squared minus 12 times 2 plus 9. That's 3 times 4 is 12. Hang on. Something is, yeah, this is fine. 12 minus 24 plus 9. That's equal to minus 3 feet per second. Okay? So that is done. And we make a bit of room. This was 9 t equals 1 second, 3 second, and we did that. So now we're told that a is the acceleration of particle x, and we want to find the acceleration when t is equal to q plus 1. What did we find? We found that q was equal to 2. Okay, so we're looking for the acceleration when t is equal to 3. Now, the acceleration is the derivative of the velocity, so it's going to be 6t minus 12. And the acceleration, therefore, at 3 is going to be 18 minus 12. That's going to be 6. All right, that's not too bad. Acceleration is going to be 6. And let's put our units 6 feet squared, or 6 feet per second squared. 6 feet per second squared. Okay. And the reason it's per second squared is because I have velocity is feet per second. And I differentiate again with respect to time, and then I get, another divided by second, which is feet per second squared. All right. Now, in part E, we want to find the total distance traveled by the particle when t is equal to q. So we want to find the integral. Remember, the distance is the absolute value of v of t from t is equal to 0 up to q, which is 3, and dt. And we know the particle changes direction at 1 and 3. So in this interval, it's going to change at 1 because we're integrating from 0 to 3. And it's a quadratic that is concave down, right, with an intercept here at 1 and 3. So it's going to be a positive velocity from 0 up to 1. And then it's going to be a negative velocity from 1 up to 3. So I put a minus sign there. All right. Now let's find what the actual antiderivative of the velocity is. It's a polynomial, so it's kind of easy to integrate. I'm going to have just t cubed. I'm going to have minus 6t squared plus 9t. That is what I have. Okay. So I have t cubed minus 6t squared plus 9t from 1 down to 0, and then minus the integral of t cubed minus 6t squared plus 9t from 3 down to 1. Okay, I'm going to start writing over here. When t is equal to 1, I have 1 cubed, minus 6 is minus 5, plus 9 is 4. So I have 4, and when it's 0, well, everything in there is going to be 0. It's going to be 4 minus 0. And then when it's equal to 3, I have t cubed is 27. Minus 6t squared is plus 54. So that's going to be 6 minus 54. 27 minus 54 is, I'll just write it, 27 minus 54. And then plus 9 times 3, that is again, it's the same thing. That's plus 27. Okay, and that all actually comes out to 0 if you look at it closely. Okay, so that is one thing. And I'm just checking that that is all good. Oh, you know what the problem is? Q is equal to 2. That's my bad. Q is equal to 2. Made a mistake. Q is equal to 2, so I was integrating up to 2. That is a pretty significant mistake. Sorry about that. Okay, so instead I was doing this from 2 down to 1. So 2 cubed is 8. Minus 6 times t squared times 2 squared is minus 24, so 8 minus 24. And then plus 18. Okay? And I'm going to subtract from that when this whole thing is equal to 1. That's the same as when this is equal to that. So it's going to actually be plus 4 again. Okay? So all in all, I'm going to have 8 minus, then I have 8 minus 24 plus 18 is 2. And so I'm going to get 6 feet. I'm going to give you 20 seconds to ask any questions you have. I'm also going to wrap up the SL content now. So standard level students, if you have any questions about any of the material, now is the time. That's all the standard level stuff that we had to cover. So from here on out, it's going to be HL stuff. So any last minute notes, questions, anything at all, let me know in the chat or the Q&A. I'm going to give you a minute, and I'm going to take 30 seconds, and then we're going to continue with the higher level stuff. Okay, so higher level content. We have a few more antiderivatives to learn. In particular, you have to know that the antiderivative of a to the power of x is 1 over ln of a to the x plus c. It's in your formula booklet. So if I have the integral of 3 to the x, that's 3 to the x over ln 3 plus c. It rarely shows up on the exams, but it's in your formula booklet in case you need it. We also know, because we know the derivatives of certain reciprocal trig functions, for example, we know that if I have f of x is equal to secant of x, then f prime of x is sec tan of x, etc. I know all of these. So if something like this showed up under an integral with a constant or a sign or whatever it is, I can use the derivatives that I know and work backwards to find the integrals, okay? So bear that in mind. These are all in your booklet too. Just remember to not just look at your integral formulas, but also your derivative formulas and see if one of them matches. You also need to know the, what's it called? The derivatives of inverse trig functions. So remember, we learned that if f of x is equal to arcsine of x, then f prime of x is 1 over square root of 1 minus x squared, something similar for arc cos, etc. And therefore, if you have an integral in a form like this, you can work backwards to an inverse trig function. Now, you also have, and it's a bit confusing because this looks a little bit like this, and it actually is. The arcsine and arc tan ones are in your formula booklet separately in general, as 1 over a squared plus x squared gives me 1 over a, when I integrate, 1 over a arctan of x over a plus c, and the integral of 1 divided by the square root of a squared minus x squared is the arcsine of x over a plus c. So also in your formula booklet. Here's an example that we're going to do. I'm going to give you a minute to get a head start, and then we're going to go over it. Okay, I think that's enough time. So I have the curve 2 minus 1 over 4 minus square root of 1 minus 4x squared. So first I'm going to have to find these x-intercepts. So I'm going to say 2 minus 1 over the square root of 1 minus 4x squared is equal to 0. So 2 is equal to 1 over the square root of 1 minus 4x squared. I square both sides, I get 4 is equal to 1 over 1 minus 4x squared. And therefore, if I take the reciprocal of both sides, or I cross multiply basically, I get 1 minus 4x squared is equal to 1 over 4. And therefore, that means that I can say 4x squared, or 4x squared is equal to 3 over 4. So x squared is equal to 3 over 16, and x is equal to plus or minus root 3 over 4. So we found x is equal to negative root 3 over 4 and positive root 3 over 4. Now, we are looking for, and I'm going to have to clear my screen now, negative root 3 over 4 and positive root 3 over 4. So that means my area is the integral from negative root 3 over 4 up to root 3 over 4 of 2 minus 1 over square root of 1 minus 4x squared dx. And that is it's going to be equal to 2x minus, and I'm going to look at my formula booklet and I realize that this 1 minus 4x squared is exactly the form for 1/2 of arc sine of 2x. Okay? And all of this is happening from root 3 over 4 to from negative root 3 over 4 up to 3 over 4. So let's start with this 2x. I'm going to have root 3 over 2 at the upper bound, and then minus root 3 over 2 at the lower bound. Okay, and then minus half of the arc sine. The arc sine of 2 times this is the arc sine of root 3 over 2. Arc sine of root 3 over 2 is equal to pi over 3. Okay, so it's going to be half of pi over 3. And then on the other side, arc sine of negative root 3 over 2 is negative pi over 3. What angle gives me a sine of negative root 3 over 2? It's pi over 3. So minus pi over 3. All right. And so this is going to simplify to root 3 minus, I have a half, but these two are going to add up to 2 pi over 3. So it's just going to cancel with the half. I'm going to have pi over 3, root 3, sorry, minus pi over 3. That is my answer. Okay. And someone is asking where I got half of arc sine of x. Well, the formula booklet says that the integral of 1 over the square root of 1 minus, what is it, a squared x squared? I'm going to check if that's the exact form that it's in. It's on the previous page here. Oh, okay, that's a good question. So it's not exactly the form. It's in my formula booklet, so maybe it's worth going over. So the form that I have in the formula booklet is the integral of 1 over the square root of a squared minus x squared dx is equal to arc sine of x over a. Okay? So what I did to turn this into a different answer is I'm going to factor out a from the, and I think isn't this supposed to be 1 over a? No, there's not supposed to be 1 over a. I'm going to factor out a from inside of the square root. So I'm going to say that I have the integral of 1 over square root of 1 minus 4x squared. I can write that as the integral. I'm going to put, I'm going to factor out 1 over 2 from the square root. So I'm going to do 1 over 2 times the square root of 4 minus x squared. Now, if that looks a little bit weird, I factored out, and I don't know why I said 4. It's supposed to be 1 over 4. Sorry, excuse me. It's supposed to be 1 over 4. So that if I put the 1 over 2 back in, now what am I saying? I factored out a 2, not a 1 over 2. Factored out 2. Okay, so I had 1 over that. Okay, and then that becomes half of the integral of 1 over the square root of half squared minus x squared. Half squared minus x squared dx. And then I apply the formula that I have with a is equal to 1/2 with a half in front. So I probably should have explained that a little bit better. Apologies. Another type of integral technique that you need to know is how to use partial fractions. So I want you to consider the integral 2x plus 1 over x minus 1 times x minus 2. I can break that down into the sum of two fractions, something over x minus 1 plus something over x minus 2. And if I put that over a common denominator, I cross multiply, do my thing, I get a plus bx minus 2a minus b. And because I know that's equal to 2x plus 1, I know that a plus b, the coefficient of x on the right-hand side, has to match 2. And then 2a minus b, negative 2a minus b, has to match the constant of 1. I can solve that system of equations. I find a is equal to minus 3 and b is equal to 5. And therefore, I can split this nasty thing into two fractions, negative 3 over x minus 1 plus 5 over x minus 2, and those I can integrate just using my normal rules. Okay, so this, sometimes you'll also have to factor the denominator yourself. You're going to have to figure out what the denominator is going to be. Okay, and notice one thing to bear in mind is that if I actually had this denominator expanded, I would have x squared minus 3x plus 2. It looks almost like I can do a substitution, but I can't because the derivative of the denominator is 2x minus 3 and not 2x minus 1. So if you're trying to do a u substitution, it doesn't quite work. Maybe think about partial fractions, especially if you have a fraction like this. Question says, is trig substitution within the syllabus or any substitution that's not explicitly in the form? Yes. So there are, any substitution could be in the syllabus, but if it is, they have to tell you what substitution it is. Either you have the integral of a form k g prime of x f prime of g of x, where you can tell kind of by looking at it what the substitution has to be, or they will say using the substitution ... Like we did earlier, I said let x equals to sine of theta. And I also, in part A, had helped you with the necessary trig identity that you would need to solve it. So any substitution can show up, but you only have to know how to identify substitutions of this form. Other substitutions will be given to you. Okay, that's the good news. Yeah, here, perfect timing. Here's an example where I give you the substitution to use. So I'm going to give you 2 minutes to get a head start, and then we're going to solve it together. All right, I think that's enough time. Let's go over this. So the question says to use the substitution u is equal to tan of x, right? So what that means is that du by dx is going to be equal to, and I actually have to check this. I don't know the derivative of tan off the top of my head, so I check my formula booklet. And the derivative of tan is secant squared. So secant squared of x. All right, and that means that dx is going to be equal to du over secant squared, okay? Or maybe it's just actually easier to recognize that dx, or simply that I can write du is equal to dx secant squared of x, because I have secant squared of x dx just immediately in the integral. And so my integral is going to become the integral from x equals to 0 up to x equals pi over 4 of secant squared dx is just going to be du, and that's going to be divided by, now with tan x equals u, it's going to be u squared plus 3u plus 2, okay? And I'm going to change my boundaries now, so I don't have to do it later. When x equals to 0, tan of x is equal to 0, so it stays 0. And when x is equal to pi over 4, tan of x is equal to 1. So I have now the integral from 0 up to 1. And that's already nicer. Those are just nicer bounds than from 0 up to pi over 4. Now, I'm going to say that, and maybe I'll do this on the left-hand side. I'm going to say that I recognize that my denominator can be factored as 1 over u plus 1 times u plus 2. So I'm looking for something, a over u plus 1 plus b over u plus 2. If I were to expand that, I would get a times u plus 2 plus b times u plus 1 over u plus 1, u plus 2. Okay, and now collecting the terms, I have a u plus bu plus 2a plus b, and that should equal just to 1. So in other words, a plus b should be equal to 0, and 2a plus b should be equal to 1. So if if I subtract those two equations, I find a is equal to 1, and therefore b is equal to minus 1. So now I can write this integral as the integral from 0 up to 1 of 1 over u plus 1 minus 1 over u plus 2 du. And that's great because now I can use my natural logs, and that is just going to be equal to ln of u plus 1 minus ln of u plus 2. And this is going to be applied from 1 down to 0. So I'm going to have ln of 2 minus ln of 3. And then minus, that's the from at 1, minus ln of 1 minus ln of 2. okay? And ln of 1 is just 0, okay? Ln of 1 is 0. And so I'm going to end up with 2 ln 2 minus ln of 3. And the answer says to put it in the form ln a over b. So that's 2 ln 2 is ln of 4. So this is going to be ln of 4 over 3. That's my final answer. Now, I think this is probably the hardest method of integration, and that's integration by parts. And integration by parts is essentially reversing the product rule. So in particular, since I know that uv prime is equal to u prime v plus uv prime, if I notice an integral which is of the form uv prime, basically uv prime, I can write that. I can say that u v prime is equal to u v prime minus u prime v using my formula, and then I integrate both sides, and the integral that I would be looking for I can write as, well, the integral of uv prime is just going to be uv, and then minus the integral of u prime v. So what has happened here is this term is no longer an integral, and what I've done is I've moved the I've moved the prime from v to u, because now it's on u. Okay, so what you're going to use integration by parts when you're looking at an integral where you would prefer where there's one thing, the two things are multiplying together. One of those things is easy to integrate, and the other thing is not so easy to integrate, but is easy to differentiate. Is the table method allowed? You are absolutely allowed to use the table method. Are you required to use the formula? When you do the DI method, you are using the formula, and I'm going to show you the DI method when I do cyclical integration by parts. It's not really useful for a straightforward integration by parts. Okay, so let's do an example. If I have the integral of x sin of x, x is easy to integrate. Sin of x is, well, it's also not too bad to integrate, to be honest. What I can do is I can say u is equal to x, and dv by dx is equal to sin of x, and that means that du by dx is equal to 1, and v is the integral of sin of x is negative cos of x. So then I write my integral as integral of x sin of x is equal to uv minus v du over dx, which is negative x cos of x, minus the integral of negative cos of x dx, which is going to just be, this becomes sin of x. So I get sin of x minus x cos of x, and that was really bad. I forgot my plus c. See, even I do that sometimes. Plus c, very, very important. Okay, let's not forget that. Now, sometimes we have to do integration by parts twice, because essentially the thing that we're going to be differentiating has to be differentiated twice before we collapse into an integral that we know. So for example, if I have x squared e to the x, I let u equals to x squared and v prime, the derivative, be e to the x. So that e to the x is easy to integrate, and x squared is going to get simpler when I differentiate it. That's how I know how to pick my u and v. And so I say integral is going to be x squared e to the x minus 2x e to the x. But I still have 2x e to the x, so I do it again. I let u is equal to 2x and v prime be equal to e to the x, and I do it again. And I get x squared e to the x minus, brackets, 2x e to the x minus 2 integral of e to the x dx. And that simplifies to something that I know. Okay, and here you could use the DI method, and I'm going to try and remember how you do that, which is basically we have the thing that we're going to differentiate and the thing that we're going to integrate. And the first thing is x squared, that's what we're going to differentiate, and we're going to integrate e to the x. And so when I differentiate 2x, x squared, I get 2x, and then I get 2, and then I get 0. Okay, and I can actually squeeze those a bit tighter together. It's going to waste a lot of space otherwise. 2x, 2, and 0. When I integrate e to the x, I get e to the x, e to the x, e to the x. And then what I'm going to do is I'm going to essentially cross all of these terms like this, of this form, in the order plus, minus, plus. And so I'm going to get x squared e to the x minus 2x e to the x plus 2e to the x. Okay? And therefore I get e to the x squared minus 2x plus 2. It's just a slightly more straightforward way to keep track of what's going on, but it's a perfectly valid method. All right? Clear the screen and continue. It's especially useful when I have a cyclical integration by parts. And cyclical integration by parts means I do integration by parts, I do it again, and I get back the original integral. And then I have to do a very weird trick of isolating the integral and then dividing by something to find the answer. So let's do an example. I have the integral of e to the x sin of x. I do my integration by parts with u is equal to sine of x and dv by dx equal to e to the x, and I get e to the x sin x minus the integral of e to the x cos x. E to the x cos x, I have to do integration by parts again. So I say u is equal to cos x, dv by dx equal to e to the x, and therefore du by dx is equal to negative sin of x. And then I therefore get that the integral of e to the x cos of x is e to the x cos of x plus e to the x sin of x. But this is the original integral I. So I get e to the x cos x plus I. And then what do I have? I now have e to the x sin of x. I is equal to e to the x sin of x minus e to the x cos of x, again minus I. So I move the I to the other side. And now I have 2I is equal to e to the x sin of x plus cos of x. I divide by 2, and I find I is equal to half e to the x times sin of x plus cos of x, all plus c. Okay? So that was tricky, and I can show you how to do this using the DI method again. DI, I have the thing I'm going to differentiate, which is sin of x, and the thing I'm going to integrate is e to the x, okay? So I integrate it, it's going to stay e to the x the whole time. This is going to become cos of x, and then negative sin of x, okay? And I'm going to stop there because basically what I'm going to end up with is, now that I recognize sin of x, that these two terms give me the same as these two terms with a sign change, I can stop there and I can write my DI method using just these first three. I can say that the integral is going to be equal to, I still do this, except the last one is going to be an integral because I haven't done the terms after it, okay? So in other words, I get sin of x e to the x plus cos x e to the x minus I, because that last thing is just going to be the integral of sin of x e to the x, and I'm going to get the same thing if I do that. All right, so the DI method still works. If you like the DI method, I would recommend that you go and watch a full video just about the DI method, because someone asked me about it today, and I vaguely remember how to do it, but someone can explain it better than you, better than me, I mean. So if you want to use it during the exams, make sure that you know how to use it perfectly, because I don't want you to like take this half-baked strategy and go into the exams. If this works for you and you seem to think this is intuitive, and to be honest, I think it's cleaner than like this long work that I did over there. If you like it, go watch a specific video about it. If you want me to, I can try and make one at some point, but I don't really have the time right now. But yeah, it's a good strategy. I just honestly, I'd forgotten it was a thing, and so I didn't put it in the slides. So now we have a little example question, and I do have to move a little bit fast, but I can give you 5 minutes to try this on your own. Okay, let's go over the solution here. So in part A, I'm trying to find the derivative of a function e to the x sin of x. I use my product rule. I have f prime of x is going to be equal to, the derivative of e to the x is e to the x times sine of x, and then plus e to the x times the derivative of sine of x, which is cos of x. And so I have e to the x, oops, yeah, that's my answer, e to the x sin of x plus e to the x cos of x. And you can factor out e to the x if you want, but this is perfectly fine. Okay, that's part A. Now, using integration by parts, show that the integral of f of x dx is equal to e to the x over 2 sin of x minus cos of x plus c. So I'm looking for the integral of e to the x sin of x dx. Okay, I can let u be equal to e to the x, I can let u be equal to sin of x and v prime be equal to e to the x. V prime be equal to e to the x, so that u prime is equal to cos of x and v is equal to e to the x. And therefore, this integral is going to be equal to e to the x sin of x minus the integral of e to the x cos of x dx. Now, the integral of e to the x cos of x dx is equal to, well, now I let u be equal to cos of x. U prime, therefore, is equal to negative sin of x. And I let v prime equals e to the x, so that v is equal to e to the x also. And this is going to be e to the x cos of x minus the integral of well, it's going to be actually plus the integral of, because I have a minus sign here, e to the x sin of x, e to the x sin of x dx. Okay, and that I can write as e to the x cos of x plus I. And therefore, this I is equal to e to the x sin of x minus e to the x cos of x minus I. And so 2I is equal to e to the x sin of x cos of x. And I divide by 2, and I get I is equal to half e to the x, or e to the x over 2 sin x minus cos x. Okay? Nice. Let's clear the screen, and we'll continue from there. Now, using your answer to A and the result from B, or otherwise, show that the integral of e to the e of x cos of x is e to the x over 2 sin x plus cos x. So let's remember that f prime of x was e to the x sin of x plus e to the x cos of x, which means that e to the x cos of x, this thing that I'm thinking about now, can be written as f prime of x minus e to the x sin of x. All right, and therefore, if I integrate both sides, e to the x cos of x dx, cos of x dx is equal to the integral of f prime of x minus the integral of minus I, with the integral that we found in part B, which is e to the x over 2 sin x minus cos x. All right, and therefore, because the integral of the derivative is the original function, this is e to the x times sin x plus cos x minus half of sin x minus cos x. So I can say this is e to the x over 2, and I'm going to have 2 sin x plus 2 cos x, and then minus sin x. And why do I have a minus there? Hang on. Did I say something wrong? Let me check this quickly. Bum bum. Okay. F of x. Oh, sorry. F of x is just this sin x part. So it's e to the x sin of x. So if I put that over 2, it's 2 sin of x, e to the x over 2 minus sin of x, and then plus cos of x minus sin of x plus cos of x. All right, and that is e to the x over 2 sin x plus cos x. And let's not forget plus c somewhere. Okay, that is the answer. Now, using all those results that we found, we're going to answer part D, which is to find the area of the region R enclosed between the function f of x and the line y is equal to e to the x cos of x. So let's first find the intersections. And e to the x sin of x, the function f, is equal to e to the x cos of x. All right, e to the x is never equal to 0, so I can cancel it. And that means that sin of x is equal to cos of x, which happens in particular since we're in this interval here, when x is equal to, I can say either, well, basically when tan of x is equal to 1, so x is equal to pi over 4 is one solution, or negative 3 pi over 4. So those are my two solutions. So this is going to be negative 3 pi over 4, and this is going to be pi over 4. So then my area is going to be the integral, and the question is which of these two functions is greater? Well, I look at the graph, and it's not really much help. I have to think about what is bigger, sin of x or cos of x in the interval negative pi up to pi, or sorry, in between 3 pi over 4 and pi over 4. Let's draw a little unit circle. We are in the interval from here up to here, so we're along this segment here. Okay, and here the cosine, is going to be larger, it looks like to me, because I'm on mostly on the positive side over here when cosine is positive. Cosine is only negative here when sine is also negative, okay? And in particular, we're below the line, we're below tan of x, and since we're below tan of x, it means that sine of x over cos of x is negative. We're below that line, and so cos of x is bigger, okay? Cos of x is bigger. Let me clear the screen, or at least clear that unit circle. And so the area that I'm computing is just going to be e to the x cos of x minus e to the x sin of x. So I can just put that like this, minus e to the x sin of x dx. Now, it is worth noting that even though I put these in the right order in this case, if you didn't put them in the right order, all that would happen is your answer would be negative. And then you could just write a note at the end that says, oh, that means that f of x is bigger than g of x, or just write which function is bigger, and you can flip the sign as long as you explain how you know, and the area must be positive, so you just flip it, and that would be totally fine, okay? So this is from negative 3 pi over 4 up to pi over 4. And this is the sum of two integrals. I have the integral e to the x cos of x, which is e to the x over 2 times sin of x plus cos of x, and then plus the integral that I found in b, which is e to the x over 2 sin of x minus cos of x, okay, from pi over 4 down, from negative 3 pi over 4 up to pi over 4. All right. Inside, I'm going to have the sin x's are going to add up and the cos x's are going to cancel. So I'm going to have just e to the x sin of x from negative 3 pi over 4 up to pi over 4. All right. And that gives me e to the pi over 4 times sin of pi over 4, which is root 2 over 2, minus e to the negative 3 pi over 4, e to the negative 3 pi over 4, times sin of negative 3 pi over 4, and that is negative root 2 over 2, so this is just plus root 2 over 2 again. And so that's an acceptable form for my final answer. I can also just factor out the root 2 over 2, root 2 over 2 times e to the pi over 4 plus e to the negative 3 pi over 4. Okay, that's my answer. Any questions about that? Nope, seems like we are good. Let's continue. So another important thing that you need to know at the higher level is how to find the area enclosed between a curve and the y-axis, not just a curve and the x-axis. So let's remember from function theory that the curve of the inverse function is the reflection in the line y is equal to x. So if I was looking for the area enclosed between a function and the y-axis, it's going to be the same as the area enclosed by the inverse function and the x-axis, all right? So I can think about, therefore, finding the area as there's two ways to do it. Either I literally reflect, I can find the inverse function, I can integrate with respect to dx, or I can do basically in the same way that earlier we sliced up the area into a bunch of rectangles with certain heights. Now I slice them up but horizontally, and I'm going to do the same thing. I'm going to integrate, but now I'm going to be integrating with respect to y. So I'm going to have an expression x in terms of y, and I'm going to integrate it with respect to y, okay? And it's going to give me the same result. I'm doing exactly the same thing, just along the y-axis. And what does that look like? Well, let's say I have the function y squared is equal to, it's not a function, a curve, y squared is equal to 1 minus x. Let's isolate it, and I get x is equal to 1 minus y squared. If I integrate that between the bounds -1 and 1, I get 1 minus y squared dy is y minus y cubed over 3 from 1 down to -1. That simplifies to 4 over 3. And I have a question about this. All right, I'm going to do an example quickly. We have an example IB problem, and we have 50 minutes left. So can I afford to give you the time? I can afford to give you the time. I'm going to give you 5 minutes or 3 minutes, 3 minutes to get a head start. That's enough. Okay, so we're going to get started on this. And I'm looking for the area enclosed between the curve y is equal to tan x and the y-axis. That means I'm integrating with respect to y, right? I need to find first an expression for x in terms of y. Let me make my pen color correct again. I need an expression for x in terms of y. I want x in terms of y. So if I have y is equal to tan of x, that means that x is equal to arctan of y. And therefore, I'm trying to integrate from 0 up to 1 the arctan of y dy. Okay, that's what I'm trying to integrate, which is the same as adding up the area like this. Okay, that's what I'm trying to do. And the question says to use integration by parts, but I don't even have a product of two functions here. I just have arctan of y. And this is a sort of relatively common trick in integration by parts, where I say that I'm going to be doing the integral. Let's say I is equal to the integral of 1 times arctan of y. All right, arctan of y dy. And that's a little bit silly, but what I can do then is I can say, well, u is equal to arctan of y, because I know how to take its derivative, and it gets easier when I don't know how to integrate it, but I know how to take its derivative. And that means I can let v prime be equal to 1, so that u prime is equal to, using this is in your formula booklet, u prime is 1 over 1 plus y squared, and v is equal to y. So my integral can then be written as y arctan of y minus the integral of, now it's going to be 1 over 1 plus y squared. And sorry, it's supposed to be y over 1 plus y squared dy. All right, and that integral itself, the integral of 1 plus y squared, I can say integral of y over 1 plus y squared dy. I have to let u be equal to 1 plus y squared, and that means that du over dy is equal to 2y. So y dy is equal to, and let me just move my face so you can see what I'm saying. That means that y dy is equal to half of du. And so I can write this as the integral of half the integral of 1 over u du, which is equal to half ln the absolute value of u. So over here, that means that I is equal to, and you could put a plus c, but it's not going to matter because it's a definite integral, y arctan of y minus half ln of the absolute value of u, which is 1 plus y squared. Okay? And so that now tells me my indefinite integral, and I need to put the boundaries on that. So let me make a bit of room, and we'll put the boundaries on that. So I put the boundaries on. I'm going to start, the upper boundary is pi over 4. So I'm going to put pi over 4, and arctan of pi, oh, sorry, what am I saying? That's the integral in part B. My bounds are from 0 up to 1, so I'm going to do 1 arctan of 1 minus half ln of 1 plus y squared, which is ln of 2, and then minus, I'm just going to have 0 for, so 0 arctan of 0, which is going to be 0, minus half ln of 1. And half ln of 1 is going to be 0, so it's just going to be 0. Okay, and then arctan of 1 is pi over 4, and the absolute value of 2 is just 2, so this is minus ln, half ln of 2. And that is what the question wanted us to find. So that is complete. Okay. Now, part B, hence find the value of the integral from 0 up to pi over 4 of tan of x. And we don't know how to integrate tan of x. And hang on, there's a question. Here, this was a show that question with a specific form. If we were doing this otherwise, is writing it as ln square root 2 appropriate? That would be appropriate. Some of them, they'll accept both unless they tell you otherwise, okay? But yeah, you could write it as ln square root 2, and that would be totally fine. Okay, so now we want to find the area enclosed under the graph of tan of x between 0 and pi over 4. Okay, so this is the curve of tan of x. This is tan of x. And let's see, what is tan of pi over 4? Tan of pi over 4 is equal to 1, which means that this is x is equal to pi over 4. All right, and therefore I'm actually looking for this area here. I can draw that a little bit better. I'm looking for this area here, which complements with the area that I found in part A to form a rectangle. And the rectangle is going to have an area of pi over 4 times 1. So the integral from 0 up to pi over 4 of tan of x dx is going to be pi over 4 minus what I found in a, which is pi over 4 minus half ln of 2. And that is equal to just half ln of 2. Okay? I hope that is clear. This is a very IB style question to kind of really work on the reasoning with the areas here and recognize this is a rectangle. It's a tricky question, and something like this could show up on the IB. Now we're almost at the end. We have one last concept to cover, which is volumes of revolution. Okay, so what is a volume of revolution? I'm going to show you in 3D here. You take the curve, which is a function, which is that orange line there, and you revolve it around the x-axis by kind of rotating it around, and it produces this solid after you rotate it by 2 pi. So you can see that happening there. And we can think about how we would calculate the volume of that solid, because it now becomes a 3D shape. So I want you to imagine that 3D shape here, and I've sliced it up into a bunch of little discs, I guess. They're not quite discs, but I've cut it up, okay, into pizza slices, but in a weird way, or whole pizzas, I guess, if you like. And I want you to imagine this orange slice here that I've isolated in the line below. All right, that orange slice has a thickness of dx and a radius of f of x. And the orange slice is roughly speaking, it's a cylinder. I don't know exactly, but it's approximately a cylinder, and a cylinder has a volume of pi r squared h. So this thing is going to have a volume of pi f of x squared dx. Okay? And I say dx, maybe you can say delta x. It doesn't really make a difference because I'm going to be taking the limit as n goes to infinity. And I'm going to be adding all of these things up. And what is a sum of things as the limit of the number of things goes to infinity? It's an integral. So this is the integral of pi f of x squared dx. Hopefully this gives you some intuition as to where this formula came from. And also I want you to be able to picture these solids and what they look like. Okay. What does that mean? Here's another example of what a solid revolution might look like. This is for the function 2 plus sin of x. It would look like this, and you can see the 2 plus sin of x there. I can zoom out also. It would continue. It makes this weird looking shape. But it means that the volume of revolution is given by, the volume of the solid is given by v is equal to the integral from a to b of pi y squared dx. And usually on the IB, you will have a function that looks something like this, that has y-intercepts, or has x-intercepts, and you're revolving this region around the x-axis, or sometimes the y-axis, we'll see that in a second, but you will know where the x-intercepts are. So it won't really have to tell you. You'll be able to find them, okay? So here's an example. Let's say I take the solid produced by 1 minus x squared, and I revolve it about the x-axis. Well, the zeros are going to be x equals plus or minus 1, so I'm integrating from negative 1 up to 1 of pi times 1 minus x squared all squared. If I expand that, I get this polynomial, and I know how to find the integrals of polynomials, and that leads me to my answer of 16 pi over 15. Okay, next slide. So with that said, we can also do volumes of revolution about the y-axis, and we're going to do really, the only thing I change is I swap x and y in the integral, because now I'm integrating my slices in the y direction, and the radius is the x squared instead of the y squared. Okay, so it looks something like this. This is one of my slices. The radius is this x, and I'm summing up, I'm integrating all the dy's like that. Okay. And I'm not going to bother with the example because it's not that interesting. Instead, we're just going to do our last problem of the day, which is an example of this. Okay, so I'm going to give you, I have time, so I'm going to give you 5 minutes to make a full attempt at this. It's not a hard one. I just want you to understand this skill, and then we're going to be done for the day. Okay, let's solve this question. So I have the curve y cos of y squared is equal to x squared. And I can see that it has a y-intercept of a. And in part A, we're trying to find the value of a. So the the y-intercept happens when x is equal to 0. Let me change the color. The y-intercept happens when x is equal to 0. Or in other words, y cos of y squared is equal to 0. Now, either y is equal to 0, which would be that intercept, y is equal to 0, or cos of y squared is equal to 0. Okay? And I can tell then, therefore, that y squared is going to be equal to pi over 2 plus k pi. Now, if you zoomed out on this curve, you would actually see that it continues and continues. But I'm going to be looking for the first solution because any one after that is going to be somewhere higher up the x-axis. And I only see one intercept here. And therefore, I can say that y squared is equal to pi over 2. So y is equal to root pi. Oh no, my iPad just died. Damn it. Here's what I'm going to do. I'm going to share my screen and show you the solution on this screen instead. It's going to work just fine. Okay, what do I have though? I found that y is equal to root pi over 2. So a is equal to root pi over 2. All right, that is part A. Now in part B, I'm going to revolve the solid produced by 2 pi around the y-axis, which means I'm going to be doing an integral with respect to dy, and I'm integrating pi x squared. And x squared is just y cos of y squared. Okay, so I'm going to be doing the integral of from a to b of y cos of y squared, which in particular I'm going to be integrating from 0 up to a, and a is equal to root pi over 2. And we make the substitution u is equal to y squared, because I notice I have this y, which is the derivative of y squared with a factor of 2 missing. Okay, so I write the integral as pi times the integral from 0 up to a of y cos of y squared, which is the integral, it's the pi times the integral from u is equal to 0 up to u is equal to pi over 2, because I'm integrating, I'm letting u is equal to y squared, so I have up to a squared, that becomes pi over 2, and I have cos of u times half of du. Okay, so that becomes pi over 2, integral from 0 up to pi over 2 of cos of u du. The integral of cos of u is sine of u, so this is pi over 2 sine of u from pi over 2 down to 0, which is pi over 2 times sine of pi over 2 minus sine of 0. That is just pi over 2. Okay, that is the answer. So I'm going to see if there are any questions in the chat. If not, I'm stopping the share. That is everything we had to cover today. I actually was ahead of schedule. I expected we'd be here until another half an hour, but maybe I went too quickly. If there are any questions, now is the time. Otherwise, I'm also going to, I'm not going to send out the poll. I poll you guys every day, and you say the same things. So any questions or comments or anything like that, now is the time. Otherwise, you can head out whenever you want. I'm going to stop the recording also in case someone wants to ask something in person. So anyone on the recording, goodbye.